By the way, this is OBS is the software he's using. It's free and it's very convenient for these sorts of recording audio and video simultaneously.
You can also live stream your course or whatever. Not that you want to do that, and we're not doing that.
Only in Mac or?
Pardon me?
Only in the Mac.
Oh no, it's any platform. So. Oh, well, at least Linux and Windows as well too. So our goal is to map that probability onto negative infinity to positive infinity. We talked about yesterday. We do this through the use of a link function. That's the title for it. So that link function really is just a function of the mean. And in most generalized models, that's how that link function behaves. So the mean. You'll note one thing yesterday. We talked about y being normal. There was no link function. It was not applied to it. Turns out, to make that a generalized model, we pretend there is a function. It's just the number 1 multiplies everything.
Identity.
It's called the identity link. Or another way of putting it, in my part of California, it is what it is. All right, well, anyway. Okay. So mostly what we will do, and actually for the rest of this class, we're going to use the logit. But there are other link functions you can use as well. For instance, you can use the probit, which is effectively where we transform the probability into what I would just call a z-score, right? How we do that is we say the probability is that we find the z that corresponds to the upper limit of this area under the curve of a normal distribution. I guess I'm going this way. And this on the web. Thanks, Siri. That's the problem. I gesture with my right arm. I'm usually wearing my watch over here. Come on, Siri.
Now playing podcast.
Oh my goodness. There we go. Less common. Now, you know about logit, and you probably heard about
It's Bill
probit.
Simmons from The Ringer, and this is a podcast called The Rewatchables. We've been doing it really since...
Okay. Excuse me. I've never taught with my watch on my right arm. I usually wear it on my left arm, and that's kind of hard right now. And so everything I do, it's like Siri is trying to join every conversation. I just need to do not disturb. Let's try that, see how this works. Okay, so we know about logit, and we know about probit. But have you heard of the log-log link function before? Log-log. Lisa, where do you use log-log? Lisa's the expert in log-log.
So one of them is for distributions in which 0 is far more common, and one of them is for distributions in which 1 is more common, and I will never ever remember which is which.
But we often don't get into those situations. One of the cases where we've used it before was when we had forced choice items, where you had to pick option A or option B, so 2 options. Again, those are dichotomous items. You can think about those items, as presenting a bit of a challenge because there's a non-zero probability you might pick one or the other, particularly if these are items that are personality-based or was it the Minnesota Multiphasic Personality Inventory, MMPI, aren't most of their items in the forced choice, 2-choice dichotomous items. So I mention those just because you may not see these in other software packages, but in Stan you can implement them fairly quickly. So you can find other ways to do that. I'm just trying to get you to say, yes, that Stan is an overwhelming piece of software, but there are benefits. I'm trying to motivate you. Not just for you, just for everybody as well. So the link function takes that probability and divides it by 1 minus itself. So that term in pink right there, that's the odds. And because odds range from 0 to infinity, the log helps put that lower part, make it go from negative infinity to positive infinity. Right, so this link function takes a probability as an input and returns a real number as its output. Alternatively, we can go backwards, and this is the form that you normally see in IRT, where we have the inverse link function. Right? So inverse link function is e to the logit. Inside the parentheses of the e term, Euler's constant, that is a continuous number that ranges from positive infinity to negative infinity, and that's what's going to take our value for our model. You may see this expressed in multiple ways. We saw this a little bit yesterday in the R syntax for MERT, if we went down, I was trying to figure out the parameterization and the help. And we remember our help really needs to be in quotes. It's like help, like ironically help, right? This is sometimes how you see it. This is sometimes how you see it. These are all equivalent ways of seeing it. I'm most familiar, and I feel like a lot of the world is most familiar with the term on the left, so I tend to write most of my notation with that version of IRT models. So that is what you'll see in this class, in this section. Okay, how we doing so far? Just getting warmed up today. Okay. So we're going to now begin with latent variable models for Bernoulli variables. Finally, we're here, day 2. We'll start with the logit length function. And we're going to begin with that linear predictor. Remember, the term linear predictor means the part that does the prediction. So it's the part, like in a linear model, like we're predicting y, it's the part that doesn't include error. Right? It's all the predictors, the intercept, and the regression coefficients. So we're going to talk about using this core right here. Sometimes I call this a kernel of a model. That is the linear predictor from factor analysis. If we predict a continuous outcome, we put error on the end. Talked about that yesterday. Today, what we just do is take that linear predictor and predict the logit of the probability of a correct response. Now, once again, remember, our items are Bernoulli, right? So the probability of a correct response, that's the mean, effectively, of the item. We're going to say that mean is conditional now on a predictor, and theta, for each person, that's our latent variable. That's going to be what we predict with. So if we go back to the world, if we pretended that we could observe a person's theta, this would just be a logistic regression where we would have an intercept representing the expected logit when theta is 0. And then we would have a slope representing the increase in the logit for every one unit increase in theta. Actually, I should say that differently. The change in the logit for every 1 unit increase in theta. As theta goes up, the logit changes by lambda. I corrected myself there because although not common in measurement models, it is possible that lambda can be negative, right? So if theta goes up 1 and it's negative, the logit goes down, right? So, okay. So we replace the mean in the generalized model by the probability. And again, we saw both of these as well. Item intercept is what we call mu. Item discrimination or slope or factor loading, your choice, is what we call lambda. And trying to teach this to a diverse audience of students, not just here, but in my class when I was teaching this last fall in Bayesian psychometric models, I just kept saying discrimination or slope, or discrimination or factor loading. I will try to use the two interchangeably. Okay. So there are a few model family names, depending on your field. It could be the 2-parameter logistic model with a slope-intercept parameterization, or it could be an item factor model. And this is the part of measurement I mentioned yesterday morning, where sort of diverging, different types of or similar types of methodology were developed in different fields. So in educational measurement, Birnbaum had a chapter in the Lord Novick textbook. By the way, Novick, University of Iowa. Just had to say that. I know, we're like rolling our eyes. Sorry, maybe I'll cut that out. Scrub that from the video. No, anyway. And then the second area was item factor analysis, which I particularly like this paper by Christofferson in 1975, factor analysis of dichotomous variables. And I would say, interestingly, estimation methods are the biggest difference between the two areas. Not in Bayes. In Bayes, both are very similar, but we didn't have as much Bayesian estimation that we have now, the methods for it, back when these papers were published. Typically, item factor analysis is, it uses a limited information estimation process. So for instance, if you use Levon and you have dichotomous items, or M plus with dichotomous items as a default, doesn't have to, but it defaults to this. What limited information means is that instead of using the entire likelihood function, which is all of the data, we use a summary statistic of the data. In this case, a tetraquark or polyquark correlation matrix. And we factor analyze that matrix. So that's where this item factor analysis tends to have a default for estimation. Whereas in not item factor analysis, in item response theory, we started with a method called joint maximum likelihood. Lord created the program named Logist in the early 70s. Joint maximum likelihood is not ideal from a statistical perspective, but shortly thereafter, once we discovered the EM algorithm, well, that became marginal maximum likelihood, and that is still today the most popular method of estimation. But that is a full information method, meaning we use all of the data itself rather than a summary of the data. And there are implications for what missing data, how missing data are assumed in each of those, and there's also other implications for parameterization, so it goes on and on and on. I'll stop here. We need to worry nothing about that in Bayes. Bayesian, what we're doing today and what we do in STAN is full information. So we will be using all of the data. Alternatively, I do believe M+ implements a Bayesian version of the limited information. But why? I don't know why. I mean, they sort of converge in large samples to the same result, but I always seem to have a better affinity for the full information methods myself.
Bigger deal with missing data.
Missing data is the assumptions of missing data for limited information are much more strict about how data are missing. Is that what you're saying? Okay. I'm on a tangent. Any questions? Okay. So long story short, for today, they're interchangeable. It's a simple parameterization usually. So differences from our normal distribution. You can see here's our normal distribution. This would be called a factor analysis, confirmatory factor analysis, or just a simple factor analysis with one latent variable. Compared to our Bernoulli distribution, you can see the kernel or the core, the linear predictor, happens to be the same if we were phrasing it in different ways. But the parameters, by the same. We can't. This is not to say that we could take the same data and apply it in both models. This is just to compare what's happening in IRT versus what's happening in factor analysis itself. There's no unique variance. This should not be phi. This should be psi. Another typo. That term, there's not this in the Bernoulli distribution. We mentioned that yesterday. And the reason for that, again, is that the Bernoulli distribution just has one parameter. That parameter represents its mean. Remember, the variance is a function of the mean, right? The mean is, if the mean is pi, then the variance is pi times 1 minus pi. So there is no place, if you want to put it, for a parameter for the variance, because if you know the mean, you already know the variance. The identity link function, I mentioned that earlier, is used in the normal distribution. I won't go too much into this, but basically there is one feature of the logistic distribution means that the model scale and the data scale are the same. Maybe I'll just leave that right now. It's a little bit too much. We use a different link function. I'll just say that. So commonly we see IRT models phrased with the inverse link function, just like this. And if we have 10 items, like in our example, it's a 10-item simultaneous regression, logistic regression model that we're trying to estimate. It's just we did not observe theta. And you're thinking, wait a minute, just we didn't observe theta, how does that work? Turns out we can figure theta out using Bayes' theorem. But we're getting to that in just a moment. So I have some steps in the typical measurement model analysis. You probably know these. We need to specify our model. Basically, what is the loading structure? What is our hypothesized structure of our data? We need to define the scale. I mentioned that yesterday, the scale of the variables. We need to estimate or figure out if we're estimating a mean or a variance by setting parameters, fixing certain parameters to values, or fixing the mean and variance to, like, say, a standardized factor. We need to estimate the model and then examine the model data fit. And then iterate between steps 1 and 4 until we get adequate model fit. Good news, adequate model fit. Who knows what that means in the Bayes context? There's not the same standard for model fit in Bayes that you see in traditional non-Bayesian methods for model fit, like in confirmatory factor analysis, like in RMSEA or CFI, TLI, those fit statistics. We have to build that ourselves. And sure, guess what? That's later this morning. We're building that too. Lisa's. You should see her face.
Yeah.
I think we just need to put your face on the camera right here.
Nope.
And have you seen these videos on YouTube? Like people reacting to your music, or we need Lisa reacts. That would be pretty funny. I actually think that would be a hit. We should do that in class. Lisa, I did an exploratory factor analysis. All right. So then there's some auxiliary components here. Okay, so we do all this. What do we do with it when we're done? Maybe you want to give people scores. Maybe you want to do something with those scores. That's score estimation or secondary analyses with scores. Somehow we may want to evaluate whether our items are of good quality, or we want to see where items are most informative about the trait itself. We can do that too. We can construct a scale itself. So in IRT, scale construction is guided by something, the topic of information. Where do we have the most information for our latent trait? We could do that as well. And in other cases, you may have different test forms. You may want to equate those two values. It's another thing we could do. Or we may also be concerned about differential item functioning, item bias, measurement invariance or non-invariance, and all that as well. So that's sort of auxiliary. And most of that we will not discuss here. But if you're interested in more of that, go to the website I have, or Lisa's website, and we talk about those in different ways. I have a more recent Bayesian version of it, and Lisa does that in the non-Bayesian sense. All right, so let's specify the model. We'll initially assume that theta follows a normal distribution, where we have a mean of 0 and a standard deviation 1. We call this a standardized factor, standardized latent variable. This allows us to estimate all of the item parameters of the model. So theta is like a z-score, right? This is not where we're going to end up, though, because as we go into the multi-level item response theory, we will want to describe how much variance of theta we're explaining based on a student's free and reduced lunch status. And moreover, we will also want to separate a school-level ability with its own variance as well, and describe how much variance of the school is explained by the proportion of students who are on free or reduced lunch at that school. That is where we're headed for. So we will need to estimate some type of variance. I put that in quotes because, remember, the scale is arbitrary. I sort of drew that slide yesterday where I had the number line and I just sort of erased the numbers. People are lined up the same, but the numbers on the bottom, it's a little weird. They may change. Okay, so we need two types of identification for models to be valid, or we need empirical identification, which is the minimum number of items to measure each variable, latent variable. So from confirmatory factor, we're doing unidimensional models today. So we have only one trait. So we only need 3 items to identify the model in a maximum likelihood confirmatory factor analysis sense. Now, I have had some very, contentious debates with some colleagues about whether that's true in Bayesian and item response theory. So Bayesian priors, the ability to put a prior on a model, allows you to sort of pretend that a model becomes identified. Because if you think about it, that prior is information that is augmenting the model data likelihood. Let me give you a case in point. Let's imagine that we wanted to estimate theta's variance. Typically, we need to fix one loading. Usually, we fix a loading to the value of 1. I, in a Bayesian sense, could say, okay, I can do that, but I'm not going to fix the loading. I'm going to put a prior on the loading, and I'm going to use a normal distribution with a mean of 1 and a variance of 0.001. So this is a really informative prior right around that loading. And sure enough, the model will run, and it will look like it converges, but it's sort of a weird I don't like that setting. I think it's sort of, I don't think the numbers you're getting are valid. I think you are still you're setting values that are, it's sort of making a prior, a subjective choice on your data that you probably shouldn't. I haven't read a lot about the differences in this. It's sort of an overlooked part, at least in the literature I've read about Bayesian psychometric models. So I want to make that clear. If you're studying Bayesian psychometric models, there's some debate as to what identification constraints are, because when we add prior distributions, we can play games or make really strange choices of the prior, informative priors, to build identification in. So what I tend to do, and then what I advise, is using the CFA standard in your work, right? The minimum number of items. Besides, can you imagine giving somebody 2 binary items and trying to estimate their latent variable? Like, that wouldn't go well. Like, with 2 binary items, there's 4 permutations of how people can respond, right? And we're going to map those onto a continuum that goes from negative infinity to positive infinity. I don't think that's really plausible. All right. Okay. The second part is, so we need a minimum number of items, number 1. And number 2, we need to set the scale of the latent trait. The standardized factor is what we will be using first. Oh, I really need to not have it do that. Standardized factors is first. Here we see this, we're going to set all latent variables to 1, the variance to 1, the mean to 0. We don't have a multivariate set of traits.
It did that by itself.
I'm wondering if the duplex is on. No, I don't think so. Is someone able to do that?
I accidentally did that because...
Oh, it's okay. That's okay. I need to compile the slides differently. I'm sorry.
Not the first time.
No.
It's just this one.
Yeah, I didn't realize they did that, and then I forgot that they did that. No, it's okay. This is all history repeating itself. So this happened in my classes last year. I switched to Quarto last summer to try to do my slides, because I thought, well, it's a learning experience, and let me tell you, I'm still learning. So there's an option I need to go and put at the top of the file when I compile it where it doesn't do that, and I should do that next time. But in the meantime, we'll just have to live with it for right now. So we have 1 latent variable. It has a mean of 0. We're setting the variance to 1. If we had more than 1 latent variable, we'd have to set all of their variances to 1, all of their means to 0. But we could estimate their correlations, right? They're off diagonal of the covariance. This is a covariance matrix of the latent variables if we have more than 1. Ironically, in our culminating lecture where we have the multi-level measurement model, we will have 2 latent variables, but they are 2 that are basically the same type at different levels. We'll have we'll have a school level math ability, and then we'll have a student level math ability, which is really a deviation from their school mean itself. But because they're the same variable at different levels, there will not be a covariance matrix between them. So it's like a multidimensional IRT model, but the variables themselves are at for different units. So it's a weird way of thinking about this from a measurement perspective. Okay, the other option that we will use later today, we may want to estimate a variance or a mean of the latent variable. For us, we want the variance. We could care less about the mean, couldn't care less about the mean. It's somewhat arbitrary in our case today, although there are cases where you might want to estimate it, particularly in measurement and variance, or if you're trying to determine whether groups differ on their latent variable. For us, to do this, for variances, we call this a marker item method. Marking the item, basically we take the 1 item and we fix a parameter to a value. We don't estimate it, we set it to a value. For variances, we often set the loading of 1 item to 1, or the slope to 1. So it would like be saying, if you remember this, this equation, this first item's lambda right here would not be estimated. It would just be a 1. And then we would estimate the variance of theta. Now, it's arbitrary which item we pick. if we pick the first item or the last item, we can still estimate theta's variance. But which item we pick will govern what the estimate of the variance is, because the variance is now a function of that item's data itself. Question?
Could I ask a super general question?
Please.
Okay, so normally in this case you will looking like you explained it first for links and response functions.
Yes.
And the link functions is the inverse of the response function. Do we face a problem, for example, if I now want to do this for the graded response model or whatever, and do they need to belong to the exponential family of distribution?
No.
Or do we can only have a certain set because we can't build the inverse?
No, we do need an inverse. We need a way of taking something that's continuous and mapping it onto the space of the data. But it doesn't have to be an exponential family, like a canonical link function in exponential family terms. It doesn't have to be an exponential family distribution at all to be estimating the model. So really, and particularly in Bayesian methods. So it's your choice of link function or choice of distribution.
But still in Bayesian context, would we need to build an inverse?
Yeah. Yeah, if it's one that's not there, you'll have to build it yourself. But it's
Okay, we would be lost if we can't build the inverse.
right. Yeah, if you can't build the inverse, it will be tricky. You need something to map that continuous. So that the right hand side of this graph here is the continuous number. So that mapping to the space of the data still has to be preserved. But most of the time, there's an inverse. I guess if you're in like an unfolding model, it may be a little bit harder, or maybe something along those lines. I guess that even the unfolding models have inverse links. So I don't know which. Do you have a distribution in mind where you don't have an inverse?
No, just in general, because it's super general, this approach. You can do everything.
Yes, that's it. You can do anything you prefer, anything crazy. Now, publishing anything is a lot harder. But you can do anything, and I think that's the approach we'd like to teach you for it. But most of the time, and if you go to any generalized model textbook, or if you look at Wikipedia, there's lots of link functions and lots have defined inverses, and so I think within that set, there's probably exhausts most options that one would like to choose. But I may be wrong about that. Or maybe you have a better idea, but.
I don't know, in these discrete distribution fields, I think we just have a few distributions we normally use.
That's right. Yeah, it is an interesting, it is also an interesting part. Like you talked about the grade response model, that's a discrete distribution, but it's still governed by probabilities. So each of the parameters are probabilities that then sum to 1. So the similar link functions that we use here apply in the graded response or the partial credit model also. Nominal response as well. Yeah, but I think it looked like you want to add.
Yeah, I was just going to add on, the choice of link and the choice of distribution are two separate things. They go together a lot in practice, but like as long as you're operating in some kind of logit, you have your inverse link. But that logit could be applied to a binomial distribution or a multinomial distribution or a Bernoulli distribution. Like basically, it's like logit, probit, and log are really the only ones that you see. But those those can be used with a bunch of different kinds of distributions.
Yeah, good question. So going back to the marker item, if we want a variance, we have to fix one of the loadings, and by fix, we usually mean set it to 1. Right? And again, if I choose to fix the first loading, which is the default in Lavon and the default in M+, if I fix that first loading, and Lisa chooses to fix, I don't know, the 8th loading, our models are equivalent in the likelihood function, model data likelihood, but our estimate of theta's variance will be different, most likely different. And that's because the variance of theta is in part of the characteristic of the item itself. Right? It's a part of the variance of the item that brings that estimate. So it will look a little weird, but remember the scale is arbitrary, right? So a lot of the other features of the model won't change. It's just that where the hash marks on the number line are change, right? We're changing how wide each 1 unit is, effectively. Similarly, if we wish to estimate the latent variable mean, which we won't in our workshop, but if you might, the same thing happens. We have to pick a marker item for the mean, and in this case, we have to set the item intercept to a value. Often that value is set to 0. Although I don't do this very often, I think it's 0. Right?
Yeah, there's a typo in one of your slides about that.
Set that to 0. And again, now the latent variable mean is in part formed by the characteristics of the item itself, in which case, if I pick the first item and you pick the 7th item, we'll have different latent variable means, but the order will still be maintained of where people are. It's just where the 0 point or where the mean is shifts. Any questions? So what we will do in estimation and stand today is we'll start with the standardized factor, but the last slide, the last model today will be the marker item to estimate the variance, because we'll need that to do the multi-level measurement model as we go forward. Okay, I've just mentioned this. The important point, I guess, that I really do want to emphasize is regardless of the choice of the model data likelihoods are equivalent. Regardless of choice of which marker item, that model data likelihood itself is equivalent. One other note is differing prior distributions in a Bayesian sense may make the posterior distributions non-equivalent. Right? But that's seldom a worry, and it's seldom it's sort of a shift that seems understandable. So let's talk about the likelihood function. Remember in Bayes' theorem yesterday, we said the probability of A given B is equal to the probability of B given A times the probability of A. That first term, the probability of B given A, is our model data likelihood. And the same thing happens from IRT, right? What we're after in estimation, this is just one factor loading here. We will do this for all other factor loadings. But for one factor loading or discrimination, the probability, what we're after is the posterior distribution of lambda conditional on y. But when we use Bayes' theorem for that, we end up needing the likelihood of the data given that factor loading. And so how we form that, because this is the only, I'm just doing this for one factor loading holding the item intercept and theta constant in this case. You can think of this as when we get to, remember I talked about the Markov chain, every parameter has to have a chance to move, to change its value at every iteration. This could be like saying we're sampling each parameter separately, and now it's the turn for lambda 1 to be sampled. The component of the likelihood function is built by taking our Bernoulli distribution, where pi p1 is that person's probability of answering item 1 correctly. Now remember, that is the IRT model, right? That pi p1 is equal to e to mu1 plus lambda 1 times theta, right? And so forth. This right here is our IRT model, and this product indicates we're taking this across all people and that people are independent. Right? So that is our model data likelihood for one of the parameters. We would do a similar likelihood for different parameters as well. If you've ever read like people talking about building their Bayes algorithm for estimating in papers before, remember this was a big challenge when I was in school. They don't ever disentangle it for one item by itself. They usually just put the full joint in, and what you end up seeing is product upon product of a product, and then prior upon prior upon prior, and it's this huge mess of how it gets there. But just disentangling it, you can do this for each of the types of items you have, and when you want to combine it into a joint likelihood, you think of which is independent and make the product form. Here we go. So the product of probabilities can get very small because every time we multiply a number between 0 and 1 by another number between 0 and 1, it gets smaller. Right? So often we take the log of it. And when we take the log of this, the log likelihood then becomes the sum of the logs. And if we substitute each person's probability function, this is what we end up with. And this is an example of the log likelihood for lambda, right? This is just what it looks like. We also have a log likelihood function for theta we could build. In this case, this is person 1. So we're looking at the likelihood, the model data likelihood, the data likelihood conditional on person 1's data. Like this is the first student in our data set. And similarly, the core of this is still the probability that student answers an item correctly, conditional on a value of theta 1. Right? So we already know there that item itself. Now this product is across each of the items. Right? Because we assume items are conditionally independent in this unit dimensional model. So what this shows is this is our likelihood and how we find theta. This is the same likelihood we'd use in a marginal maximum likelihood estimate for theta. It's the same. All right. But if a person answers, this is another example from that class. If a person answers, if you're just using the data likelihood here, the same problem occurs. You may have heard of this before. There's some response patterns for which there is no maximum likelihood estimate of theta. Usually it's just the case where a person answers every item correct or every item incorrect. Have you heard of that issue in IRT before? So oftentimes this is a likelihood that does not have a maximum. It's continually increasing as theta gets higher and higher. This is a person who answered every item correctly in the data. And so oftentimes the remedy for this in maximum likelihood world is to say, well, let's put a prior on theta, or let's set a boundary as to what the maximum theta should be. Depending on your use case of this. In scientific studies, the prior tends to be the prevalent use. In the United States, where the testing industry makes billions of dollars, they don't know much about this stuff, so they just draw a line and say the maximum theta is 4 or something like that. However, here's a thought experiment for you. When you put a prior on theta, right? If you look at your analysis, you look at all the people, let's say, who have answered the item correctly, their estimate, their EAP, their mean estimate of their posterior distribution tends to be the same at a limit, at a ceiling. So when you put a prior on, you're effectively doing just that, arbitrarily putting a limit to theta. But that limit, where that limit lies, is a combination of the prior that you choose and how much data exists. So it's a weird thing. So I guess what I'm trying to tell you is a prior is equally arbitrary as a choice compared to making a fixed distinction. Yes?
But that's kind of a ceiling effect, or
That's exactly it.
this may be too easy. But could it be the case that we can't differentiate then between a person who answered one item wrong and a person who rightly answered all items?
Not usually. I don't know. I don't have the proof in my head for that, but I do. Generally speaking, if most response patterns are identifiable, have a maximum in their likelihood. I don't have the proof to tell you that. So we usually can distinguish a person who answered everything correct from one who didn't. The question is just how much can we distinguish it by? And if we set a prior, the prior will put a ceiling and a floor. But the opposite to that is to arbitrarily define the ceiling and the floor. So the point I'm trying to make is the prior is also an arbitrary choice. Right? If you're putting something in that puts a ceiling and a floor in, whether it's hard coding a number or saying I'm using a normal prior, they're both a ceiling and floor, but they're both a choice, an arbitrary decision. And it's difficult to figure that out. It's one of the weird parts. I know when I was in school learning about this, people would say, "Oh, the fix to this is a prior," and it's like, really, is it a fix or is it still an arbitrary distinction? I don't know the answer, but this is a person here that has answered at least one answer incorrectly. All right. Any questions about this? The logic behind all this? Don't ask me about my logic. There isn't a whole lot. I'm working on it. Yeah. So let's talk about implementing Bernoulli outcomes in STAN. I went from just super exciting to even more exciting, right? No, that's okay. Let's talk about, so yesterday I talked about the 3 different blocks, data parameters model. And what I wanted to emphasize was when I build a set of stand code, I have this algorithm in my own mind that I use to build the code, and I start with the model block, which is the third block in syntax. But I start there because the model block helps me define the parameters that I need for the parameters block, and it helps me define the data which I need for the data block. So let's start with our data. Here we have our items right there. There are capital N items. That's my term. So we have 10 items. But I'm calling that capital N items because I'm going to make this code general. So if I change my mind and I want to drop an item, I don't have to recompile stan or change the stan code. So N items I already know is one of the data that I'm going to have to send stan. I'm going to have to tell it how many items we have. We have y for each item here. So y is like a vector. It's actually an array, which is a little bit different than data that we'd see before. So each item, you see there's not a distinction for person there. Person is actually going to be assumed. Right? It's part of the vector itself. So this is all the people for y right here. And there's a function in stan called Bernoulli logit, which is actually quite nice. I don't have to go and form or put in the logit link function, the inverse link function. I don't have to take the internal part. Basically, Bernoulli logit takes whatever in the parentheses and puts it into the inverse link function for me. It's e to that pink term divided by 1 plus e to that pink term. That is what is nice about it. It cuts down on code. For a lot of the different distributions that you can use in stan, they have similar embedded link functions for the canonical links that we would have, sort of the more popular link functions that we use in data. So Bernoulli logit is great. But inside Bernoulli logit, I have an item intercept for each item. So we know we have to define that as a parameter. I have a lambda for each item. And then I have theta. Now theta, again, we have in our data 3,100 people. So there's actually 3,100 thetas. But we don't have to put a block on the index for it. You can, but you don't have to. So this is one of the other features of stan. This is a loop across all of the items. So in all 10 items, we're going to basically be defining the same model for. You'll see other people's syntax where you will have two loops, one for item and one for person. And then in that case, you may see theta has a bracket around it to indicate which person it applies to. But generally speaking, this is code that stan has this. Okay, we're going a little too much down off the deep end here. But stan runs kind of slow relative to maximum likelihood algorithms. And one way to speed it up is to use code that's quote unquote vectorized. I don't know if you've heard that term before, but basically to do operations on vectors and matrices. So in theory, this should run a little bit quicker than code that might go element by element. But I actually think that the compiler also tries to auto-vectorize a lot. So don't get into the weeds on that too much. So what are the data pieces that we need to give stan from this code so far? I already talked about n items, and I have y. All right, so I have to give it a matrix y, and I have to have n items. That's the input into stan. Any questions so far? Okay. Now, what are the parameters? Mu is a parameter, lambda is a parameter, and theta is a parameter. So with all those being parameters, I can specify prior distributions for all. And so my prior distributions, let's start with theta. I mentioned before I'm going to start with a standard normal prior distribution. So theta follows this normal distribution. That's the same normal that we saw yesterday for y, just theta uses it now. Mean of 0, variance of 1, standard deviation of 1. Stan's normal distribution for univariate normal, the second argument is standard deviation, not variance. It's a little bit frustrating, but that's how they work. So this is theta. that applies a normal 0, 1 prior to all the thetas. For us, all 3,100 thetas with just that code. Now we also have a lambda prior and a mu prior. And this is where I switch over. I like to use a normal distribution for both of these variables priors. And here's why. Let's think about what the range of mu and lambda could be. Right? They're both real numbers. They can be any value. Right? So I don't want to constrain those values because it's possible we have negative values of mu, and actually we will observe negative values of mu, and it's possible we see negative values of lambda, particularly in more complicated models or if we forgot to reverse code data. So what we will use for prior is a multivariate normal. Right? So if we have 10 mu's, a multivariate normal is like saying there's 10 univariate normal distributions for each of them. And here, the multivariate normal has two sets of parameters it uses. It has a mean vector and a covariance matrix. The mean vector has each item's mu mean of my prior. Right? And the covariance matrix, the diagonal of that has each item's mu's variance of my prior. And the off diagonal of that would be a covariance between the two. If I thought somehow there was a relationship between item 1's intercept and item 2's intercept, I could encode that in a prior. I don't know of anybody who does that. So, multivariate normal is just a trick to write less code. I'm going to keep the off diagonal of the covariance at 0. I'm going to create a prior mean of 0. And I'm actually, for most of what I do in models, I don't like informative priors. I told this to you yesterday. I would prefer mu to have a very uninformative prior. So often I set the mean for each item to 0, and I set the variance for each item to a very large number, like 1,000 or something like that. Something that wouldn't be on the scale. Let's think about, actually, we talked about a little bit this yesterday, setting priors. The scale of logits is somewhat interesting, right? Remember, the logit is the log odds of the probability of a 1, right? And a logit of 0.5 is 0. So a logit of a probability of 0.5 is 0. A logit of a probability of 0.99. Does anybody have an idea what that is? Siri, get out here. Hang on. Let's do this. 0.99 divided by 1 minus 0.99. Take the log. There. So a very high probability has a logit of 4.59. A logit of 0.01 has a probability, or has a probability of 0.01 has a logit of negative 4.99. So what am I doing? I'm trying to give you the range of where you would expect values to be. Right, remember, the item intercept is the logit for a person with a theta who has 0, at 0, right? So if we can think of a person of theta of 0, if the item intercept's above 4, this is a person that almost everybody's, this is an item, or almost everybody's answering it correctly. And if the item intercept, or if it's below negative 4, it's an item that's very difficult, right? Everybody answering it incorrect. So why I'm mentioning this to you is, what is the scale of a normal distribution for a prior that I need to set? It needs to be somewhere where the bulk of that distribution is somewhere between, I'd say, 4.5 and negative 4.5. So if I use a normal distribution, right, centered at 0, but make it with a variance of 1,000, right? It fits that range, and it does not have a lot of information. It doesn't adjust the parameter much in that range. You see where I'm going? Yes.
Maybe I'm confused, but a negative item discrimination, it means we are totally off, or?
Yeah, there's...
if I have a low ability, I will solve the item.
Yeah, I'm right now talking about the mean, intercept of the item. But yes, a negative discrimination oftentimes we don't want them. But when we get to complicated models, they can appear. Or in personality data, if you reverse code items, if you have a negatively worded item, like, I don't know, if you see classic survey literature where you have an item where you typically, in old school statistics, we take the number and invert it, right? Change it, and you forget to change it, that will be negative, most likely. Or in a bifactor model, that happens sometimes too. So anyway, what am I talking about here is I'm trying to show you when choosing a prior, we got to consider the range of the parameter, and the item intercept mu, we know will be most likely somewhere between 4 and -4 on a scale. So we need a prior that sort of lets that happen. If I stick a strictly if I chose, for instance, a prior like a log normal distribution, a log normal distribution is only positive. That would be a bad choice of prior, because I would expect some items to have negative item intercepts. Right? Okay. For lambda, it's similar, although lambda itself, the item discrimination we just mentioned, is likely to be positive. If we've done everything the way we expect it to, it may be close to 0, but it's likely to be positive. However, we don't know. I always, the person I learned the most from in grad school is Rod McDonald, and about measurement, and he always sort of trained me to believe this way, like the fact that we don't want to restrict it to be positive because there's information in it being negative. It's diagnostic. Either something's wrong with our data, something wrong with our model, or some weirdness is happening that we need to investigate more. So for lambda, you may be inclined to put a strictly positive prior on lambda, but I choose not to do that myself. In fact, I think that you will find most people who write about this, there's a good book I like by Roy Levy and Bob Mislevy, Bayesian psychometric modeling, where they do restrict lambda to be positive. But I don't agree with it. I mean, it's usually not a big deal in educational assessment, but in personality assessment and other types, I think it becomes a big deal. So I like to keep this negative. So let's talk about its range. Question, I apologize. Well, who wants to go first? And I'll come to you after he's done.
Maybe what I'm going to say is specific to JAX, but at least from my experience, when I don't constrain lambda to be positive, then I get this sign in deter.
Yes. Yes.
So yeah, it's just convenient to
Yes.
Do this constraint sometimes.
Let me talk about that.
Old school. Chalkboard.
You mind if I use a chalkboard? Is that okay? Okay. The problem is mentioning is we have lambda times theta is actually equal to negative lambda times negative theta. And in a Markov chain, as we saw yesterday at the very beginning of the chain, we randomly start and our parameters sort of find their way to the mode or the center of a posterior distribution. Because this is in effect, in our sense, our distribution will have two modes for lambda. Something like this and something like this. Where the center of this might be our point estimate of lambda, and the center of this one might be negative lambda. So they're reflected about 0. Right? And so if we start our Markov chain, one Markov chain here, it'll wiggle around, but eventually get pulled into this mode. But if we start our Markov chain here, it'll wiggle around and get pulled into that mode. And wouldn't you know, the same thing happens to Stan as well too, almost always. So can you think of a way that we could perhaps trick Stan to otherwise not have that happen?
Starting from positive.
Bingo.
But, yeah.
That's what I do. So I start, I use a random start that's strictly positive for lambda.
But then if the fact if let's say we forgot to reverse that item, and if we force it to start from positive values, and if it goes to the other mode, then wouldn't we be full trick this item?
Well, if it's one
then
item,
the other items will be.
that's it. That's it. So it's for one item. This is the case. The other trick that you can do is ensure that we put a starting value for theta in the direction that we want lambda to go. So what do I mean by that? So I actually have those two tricks I have in the syntax. I'm going to show you. But yes, this is an enormous problem if you don't consider that. And the reality is, the problem is, we don't see this in the linear model. Like if we observe the predictor, we don't see it because we have a value for the predictor. It's a hard-coded number. We're not estimating it. But because we're in a psychometric model, it's a problem. So very good question. Thank you. Your question, please.
Yeah, I had the same question, so.
Thank you, Viola. Very good. Yes. No, I agree with you. And actually, I can't tell you the number of times I've had this problem happen as well. And actually, if you go to my class slides, you'll even see it. I plot the ICC with theta in the right direction. You'll just see the different chains. You'll have this crossing over of the ICC for each. But I'll show you my trick to get it started. The reason I believe in this trick is because, remember, where we start, lambda, is irrelevant because eventually we'll converge to a mode. And my trick is mostly effective, I would say, but not always. It depends on the data a little bit as well too, but it does do that. And it depends on how many items you have. So yes, if most of the items are positive and one is negative, then this trick works well. If you have a lot of negative ones, it may not. So good point. Okay. So once again, mu, multinormal prior, mean of 0, very large variance here. Lambda, I'm staying with a multivariate normal. I usually keep the mean of my lambdas at 0. Let's talk about that for a little bit. If I put a prior on lambda, we assume lambda is positive, right? If I choose a prior where the mean is not 0, let's say it's 2, right? As lambda increases, what happens to my trait, my theta? I get more information on it. So I have this philosophy when I code Bayesian statistics that I want to do a conservative approach to priors. I want to have data dictate, or if my prior is informative, I want it to be informative such that I am having less information about theta than otherwise. I don't want to put artificial information on theta. So think of it this way. I didn't talk about information functions yesterday. I didn't go into detail with it. We don't have the time this week. But the information for theta, the steepness of information is governed by lambda. Right? The location is actually at item difficulty, but the steepness of it, how much information is governed by lambda. So if I put a prior at 0, and let's even say if I then make it informative, let's say I make it a variance of 1, then what I'm doing is taking lambda and pushing it towards 0, right? So by default, what I'm doing is if I'm going to put an informative prior on lambda, which sometimes I might have to, depending on how complicated my model is, I would prefer the prior to err on the side of less information about the trait, because then I feel like I'm being conservative in what I'm doing with an assessment or with the data analysis. So my prior for lambda, you may sometimes see I have to put a prior where I have a variance of 1 perhaps on it. But I almost always, I don't think I could say always with this. I'm pretty sure 95% confident I'll always use a 0 mean for prior. There. How are we doing? Questions? Other questions? All right. Let's go to the parameters block. Theta, mu, and lambda. Those are the parameters. We already saw n items we needed, number of items, as a piece of data. We also needed the number of observations for theta. Now remember yesterday when we defined a vector, in Stan, a vector is a floating point number. Right, so each of these values is a floating point number. All right, real number. And then the data block will contain, actually, one thing I forgot to mention, this prior mean lambda and prior cov lambda are going to be pieces of data that I send to Stan. I'm not hard coding the prior in. And the reason for that is, if my model fails to converge, one of my remedies for that is to make a prior more informative. And if I input the prior, remember the term for this is hyperparameters. If I put those priors as the data, that means I simply have to change my data and rerun the analysis. I don't have to rechange Stan code to do so. So in my data block, you'll see the number of observations, that's an integer, number of items is an integer. And then now y is a bit different. And this is another part of Stan that's a little bit aggravating, I would say. I mentioned before, vectors and matrices are real numbers. So you cannot use a real number with a Bernoulli distribution because a Bernoulli distribution is only on zeros and ones. Despite the fact that you could have all zeros and all ones as real numbers, Stan won't let you do that. Instead, to use a Bernoulli distribution, you have to have an integer. So how do you make a matrix of integers? In Stan, you have to define what's called an array. And this is the crazy part of the array. The order of rows and columns is switched. Items comes first. We loop over them. They're column major. I believe that's what we call here. And then observations comes second. So it's like a transpose of a data matrix. It's frustrating.
Why?
Exactly. No, that's why. Sorry. Yes. Why? The array, yes, I don't understand why, but it's there.
Job security.
They're paid by IES. And the Institute of Education Statistics paid for Stan for the most part in the United States. I mean, there's, I think, some NSF funding as well, too. But all right, array. So we have an array. We define its shape here, number of items by number of observations. Then we have to tell it the type of data that's in the array. So this is an integer. And although it's optional, I do define it to have an upper and lower value. Lower of 0, upper of 1. That keeps me from accidentally having data that might have a different code in it from running. Stan will break with the Bernoulli distribution anyway if it doesn't get a 0 or 1. So if you coded your missing data as what, 99 or what's I don't know. What's SPSS used to do? It's all NA for R, so it doesn't make a difference. That's why. And then we have our matrix of means for mu. We have our matrix of covariances for mu. These are the vector of means is just number of items. The matrix of covariance is items, n items by n items. We have our vector of lambdas. Means for lambdas, prior means, and our vector of prior covariances for lambda as well. And yes, these are row major. Arrays are row major, meaning the items of persons. So to loop over an array, you have to loop over the rows of the array, which is what causes all sorts of weirdness. Okay. Questions? So building the model data in R, I use the following syntax. Remember, we build a list of all that data. And I start and I literally copy this section into R, and I have to match all the names. So the number of observations is the number of rows of my modeling data. Number of items is 10. Now my Y, I have correct response data, which was persons by items, right? So 3,100 people by 10 items. But remember, Stan needs it backwards. So that T function transposes it, just changes it over to a 10 item by 3,100 person matrix. The prior mean I set to a value of 0. The prior covariance for the items, I guess I set 10 to the diagonal. So what this does, prior mean, the rep function just makes 10 zeros in a row. The diag function creates a diagonal matrix with 1 down the diagonal, like the identity matrix. So if I multiply that by the number 10, it just puts 10 down the diagonal. And I do the same for lambdas as well. Any questions? Okay. Now, let's go over to the syntax. So this is the syntax that I was mentioning previous. Well, no, I'll stand here and try this. Okay. The first model I have for you is actually the one parameter model. All right, the one parameter model has a single lambda. We have our parameters. We have our one lambda. You see the same. This is largely the same syntax from before. The only difference is with a one parameter model, I'm building a one parameter. Let me tell you the modeling sequence here. I'm going to run a one parameter model. I'm going to run a two parameter model that has a standardized factor. And then I'm going to run a two parameter model where I have one lambda set to 1 to estimate the variance. And then I'm doing these three models for several reasons. Number one, I want to talk about how we assess model fit. Number two, I want to talk about how we do model comparisons. So having three models to compare between makes sense. You can probably guess the outcome for this. These data will not fit a one parameter model as well as a two parameter model. Whether it fits the data absolutely, I don't think it does, but we're just going to continue with it as if it did. Okay? The one parameter model is the code here, again, just one lambda, but, oh my, how did I fix this? Yeah, no, that's right. No, I don't. No, I have one lambda and I set the theta to standardized factor. That's it. Either you fix all the lambdas to 1 and you estimate the variance of theta, or you have one lambda, and lambda squared is the variance of theta. So never mind. Okay, we have everything else mostly the same. Again, the prior for lambda is just 1 because there's one of it. It's just the normal distribution, so I don't have a vector of other observations. So here, if I go to that unidimensional R model, start running my analysis here. By the way, this very first function at the top, called build tetrachoric, PPMC, that is what we're going to use for model fit checking, which will come up in the next section of this lecture itself. We're going to use tetrachoric correlations to check whether or not we have local misfit for our data. Install the packages, load the modeling data. I build my correct response items here. This is my data. Nope, that's not it. These are my data right here. So you can see I have 10 items. All those are binary. And then this is a 3,100 row data set. So number of items is 10. Number of observations is 3,100. You can sort of see it down here at the bottom of the console window. Okay, we already did the non-Bayesian analyses. Now I have this run stand function here. If you don't want to run stand but you want to follow along with this, if you keep that as false, it won't run stand. It will just load the data file for you. So you can go to fast forward to the end for it. But for stand, I want to walk through the process and show you how this works. You have I have my stand file here. Once I build the stand file, what do I have to do next before I run the model? Wait, remember? Compile. So this function CMD stand model compiles the stand program. You're going to see it's thinking about it. This actually takes a little bit of time to do. Just want to walk through this now. I won't do this for every model, I promise. It also gives you warnings. The warnings can be ignored. That's a compiler issue. So remember, Stan is making C++ code. Well, it turned out the C++ code, some of the code they use some deprecated libraries or other attributes in C++. Not a C++ expert, can't tell you what that is. But that's not a problem. It ran, and so it's compiled. So now, this Model 1PL stan is an R object, and it has a set of, it's what we call an R6 object. So it actually contains data and functions in the object as well. Our 6 objects are a sort of relatively new attempt to bring object-oriented features to the R world a little bit more, some inheritance features and polymorphism, but anyway. So the stand data itself, this is the data list I needed. So here, if I match this with my stand code, see each one of these names in data show up here in my list as well. All right, so all of those values are there. Now, this is where my trick to start is less random than normal. I'm going to create a starting value for theta. And this is a 1-parameter model. So the 1-parameter model, there's a big connection to there's a sufficient statistic for theta turns out to be the sum score. So if I create a sum score for my theta and standardized it, I can use that as a starting value for everybody's thetas to estimate the model. And that's what I'm going to do here to keep that 1 lambda parameter from flipping negative. So this is one of my tricks. My starting theta, I take the sum, find the mean, find the standard deviation, and then standardize it. So start theta looks like this. Those are my starting thetas for each person. It's the standard z-score of that. I am running this model. By the way, this random number seed is the date I started this. You can tell I started this over a month ago. I've been trying to build your stand code for a long time, at least for the workshop, and I still, anyway. I'm running 4 chains because 4. And Viola, you mentioned because I have 8 processors, so it fits nicely in a number divisible. I have give it my data. I'm running 4 parallel chains. I'm only running 1,000 warm-up chains. Yesterday I ran 10,000 warm-up, 10,000 sampling. That is way overkill usually. You don't need that many. So I'm just running 1,000 warm-up, 500 sampling. And this init function is how I choose starting values. So now I'm telling it to use for theta, use the starting theta that I have done. So think about what I'm doing. All the thetas are not starting randomly. They're all starting in the direction of where the model should be. And I'm doing that because I have a knowledge of the model that allows that to work, right? I know, again, the sufficient statistic for theta is the sum score itself. I've just standardized it to be on the scale of 0, mean 0, standard deviation 1. So to me, this is not cheating. I know this model very well. It's a very simple IRT model. So I'm just pointing Stan in the right direction of the mode I want to go to. So I run this, and this is what happens. It takes a while. So I'm at iteration 1. How's it going? Anybody want coffee?
Time for a bathroom break.
Yeah. Actually, we're getting close to break time. But you can see now I'm having it. It reports out every 500, every 200 draws or so forth. Every 100 draws, it's updating. You can actually tell it how many you want to show. But this is common. Now, this is taking a long time. It's taking a long time in part because I'm estimating each person's 3,100 thetas. So each person's theta, 1 lambda, and 10 item intercepts. So what is that? 3,111 parameters it's estimating. So for each parameter in the model, it is trying to figure out, it is proposing a new value, calculating likelihoods and priors, and transition probabilities, and then accepting or rejecting as it goes through. So all things considered, while this took a while, that's a lot of things to do all at once. You see, it was reporting each chain separately because each chain was running on a separate core of my machine. So within a chain, it's in serial. Like it's running all 3,111 parameters for one iteration, followed by another. But each chain itself was separate. And now it finished. So finally, we can see some results. The Model 1 summary. This summary object tells us what is in the data. If we run it, though, it's quite verbose. So first of all, what's happening when we do this? So Model 1 PL samples is the object that has the chain in it. It also has a summary function. So when I run this function, it's like doing nothing. That's because for every single parameter in my model, and any auxiliary statistics that I've created, it's calculating summary statistics for. So I didn't tell you this, but at the bottom of my stand code is the PPMC code for model fit, and the weighted or the log expected posterior density code for model comparisons. So that is what slowed this down even more, and that's what's slowing this down, because if I don't restrict summary to just the parameters I'm concerned about, it's going to be calculating posterior means, standard deviations, R hats for everything. But we'll see afterwards. What I ended up doing in this is I actually, for every one of the sampling iterations, I had it calculate, again, each person's person log likelihood, including prior, log posterior density. And then I had it simulate data based on model parameters as well. So not only do I have all the thetas and all the item parameters, I also have, for each chain, 500 data sets of the same size, 3,100 by 10, all built in.
You gotta say another microphone.
Oh, sorry. Yes. So I'll cancel that. I thought I could ramble just enough to get that to finish, but that's not going to work. So let me just load my output. Uh-oh, I did not put the models back, did I? Okay. Well, this is just going to have to do this. Be just a moment. So, any questions as this goes on? Yes?
Yeah, just kind of a random question. Do you ever try to compare the estimated parameters, for example, to the marginal likelihood estimation?
Yes, yeah, I do.
Would it make sense? Because I could say as a frequentist fan, oh, don't do it. It's correlated by 0.99.
Yeah, it would be great. You could. I didn't in this example, but you could. I don't see anything wrong with that. I think the only question would be is how, in the frequentist, you would like to see things that are correlated. If it's not, particularly a simple model like this, you'd like to see them correlated. If they're not, it's a little weird. Where I will typically find differences, again, for simple models like this, if I put a very informative prior on, yes, I see big differences, obviously. The other part is sometimes the frequentist version of the standard error for each parameter does not align with the Bayesian posterior standard deviation. And that's in part because of the sampling process, and in part because of some of the assumptions in the frequentist standard error formation. Any other questions? I got to get story to talk about. How many of you went on the tour yesterday? Was it good? Yeah? It's all right. Trying to like waste time here. This is. I should have planned this a little bit better. I'm sorry. This will be done in just a moment. 12. Oh, yeah, it's done now. Okay, so now I have my summary statistics. Let's take a look at those. First, let's take a look at lambda. So the summary itself, 1PL summary, is a massive data set, data frame. Right? This is the object itself. So this has every person's theta, their posterior mean, median, standard deviation, MAD, their 90% credible interval, and then their R hat, and the effective sample size for each. So we have a fairly large bit to digest. For us, I find the first thing we need to check is the convergence. And the object itself has so many other terms in it that I didn't told you about that I'll tell you about after the break, that really I need to make sure mu, theta, and lambda all converged. So I'm only going to select the part of the variables that have mu, theta, and lambda in their name. To do that, I'm using something called the grep function. grep picks out variables with that in, it uses this old regular expression syntax. So we can figure out the maximum r hat for all the mu's, lambdas, and thetas. Remember yesterday, this is how I quickly assess convergence. I have an r hat maximum of 1.01. I almost want to cry when I see that number. That's beautiful. That's just joy. Because I don't have to wait anymore. It's done. It converged. Hooray. All right? That's a good sign. So I think we've achieved convergence. If you want to take a look, you could plot, for instance, the Markov chain for, oh, I didn't save it. So the summary function gives you the summary. You can also grab the Markov chain itself with the draws function. So it will grab out all of the posterior distribution itself. So sometimes we like to plot that. This is not necessarily needed, but I'm going to show you the trace plot for lambda. This is the Markov chain for our single factor loading or discrimination parameter. Does that look okay? What do you think? It's like the Rorschach test of Bayesian statistics. You tell a lot about your personality for how you feel about convergence. No, that's not true. This is more typical of a model. Like yesterday when you saw that big mess of a plot, remember, we were just estimating a mean. It's hard to get a simpler model than just estimating a mean. Okay? So that mean plot, that thing is going to be always the best. This is pretty good. Why do I say it's pretty good? I don't see much of a trend, right? And the amount of variation doesn't seem, I mean, you sort of, the variation in how wide it goes, variation in variation, if you will, seems almost not necessarily predictable. So I find that to be fairly decent. Also, you can plot the density of it. Uh-oh, what was that? No.
Just said it's a little bit like a Rorschach.
Yeah, that's right.
What do you see in this?
That's exactly right.
How do you see that?
This looks like a witch's hat. So, interestingly, you can see it's a bit misshapen on the sides, right? It's not perfectly symmetric. It's not perfectly smooth. Part of that is because I only ran the chain 500 draws post warm-up. Right? If I wanted to smooth this some more, again, we're basically talking about distributions of order statistics, right? If you think about this is like the 90th or 95th quantile, and I want to make that a little bit more regular, I need to sample it long enough to get enough draws in that region to make it look a little more regular. But generally, we will describe this with its posterior mean. So there's that. Let's take a look at the values. The lambda itself, you can just see the summary. The estimated value is 1.62. The mean and median are identical to 2 decimal places, so it tells you it's not super skewed. And we have a posterior standard deviation. The R hat said it was converged. The credible interval is also between 1.56 and 1.67. Is this a good lambda, a good item parameter? I guess. For a 1 parameter model? Sure.
What's it?
Where? Oh, when I print out the summary, R will limit the number of values being printed to the console, and I don't want it to. So I only have 1 value here, but I have a habit of making this in my code because I don't want to only see part of the story. Let's take a look at our item intercepts. Here are the item intercepts. Okay. Our hats look converged again. Actually, very converged. We have our item values here. So remember, the item intercept is the expected logit for a theta of 0. So to interpret this, we would say a person who's, remember, theta of 0, that's the mean theta. We set that mean to be theta 0. So that means a person who is at average ability, in this case mathematics ability, this was a mathematics exam, the first item, they would have a negative log odds of answering it correctly. So that case, sort of a hard item, right? Hope I'm getting the math right arithmetic is difficult for me, like the direction of things. Anyway, so the hard items were the first 5 items of the exam, and some of the easy items were here. So to think about that, remember, we need to convert logit back to probability. So what I'm saying is exp of negative 1.59 divided by 1 plus exp of, that is the probability. Oh, yeah. So a person of average ability has only a 16%, 17% chance of answering the first item correct. And that's what it's saying. Okay. So apart from that, you can see a distribution range. This sort of maps on to one of the plots I showed of the data at the very beginning of the section yesterday, where we had the classical item difficulties, and there was this sort of separation. There was a group of items that were hard, a group of items that were easy. That's this right here. Turns out I may have done a little data snooping when I put this data set together. Make a nice range of items. Any questions? Should we do the 2PL quickly before break? This time I will not let Stan run. I will load the data. Let me show the 2PL Stan section first. By the way, one thing I wanted to note, you'll see this is my my folder. This is the files in my folder. This very first file here, model 01, model 01, is the compiled executable from Stan. That's a standalone program itself. You don't even need to run it from R, but it's the part that Stan builds on its own. Stan will clutter your disk up if you're not careful, so I end up trying to delete them. The other part I will note is if you need to recompile Stan code, it will delete it and put it together before, but it will overwrite that file. However, if there are no changes, so what Stan does, if I were to run this line again to compile, since I didn't change the Stan code in the first place, it will tell you, hey, your model executable is up to date. It won't recompile. So if you accidentally run the R code again and didn't change anything about Stan, it won't waste your time as much. It may waste your time on sampling, but not as much on the R code. Okay, so this will go a little bit quicker. This is the syntax from my slides, where lambda, now we have a lambda for every item. And here you can see lambda is a vector in parameters, meaning it now needs a mean vector and a covariance matrix. And so we go into our file here. We then would have compiled it. I'm not going to do that. We are then going to build the model, the data list. This is the same data list I showed you in the slides. And again, I'm using my starting theta trick. I didn't actually trick the lambdas on this one. So I'm just doing the thetas, keeping theta being positive. Now, theta is not sufficient statistic. The sum score is not sufficient for the 2-parameter theta, but it's sort of in the same direction. So this keeps us where we need to be. And for this, no, I didn't. Okay, let me just do a little bit of inspection. Here I am forgetting to have put this back to where I needed it to be. Sorry, I feel extra inefficient as I'm doing this with like one thumb, 9 of my fingers, right? And so it's like, welcome to the life that I've had lately. I'm a little better than I used to be, but not quite all the way there. I realized, let's see if GitHub Copilot will come to the rescue. There it is. That's why I use it. Have you tried GitHub Copilot before? It's pretty sweet. Like it just filled it, because I had done this in code above and it saw that I changed the model 2, it's like, oh, you probably want to do this again. So here I am submitting to the AI overlords already. Okay, So now I just loaded the result. Let's take a look at convergence. This is, again, using the same convergence, mu theta lambda. If you want to find the max, you have to put in the remove NAs, because there are certain parameters, there may be certain constants that are in the output that are NA, like it can't take a variance because it's constant. So the maximum is 1.01, so still converged. We can take a look at, let's see here, the trace plots. This will plot for just a moment. These are all the lambdas, all 10 lambdas. There we go with our test again. Anybody see anything suspicious? Nah. Our hat tells us what we need to know mostly, right? There's a few outlying values, but again, this is a stochastic process. There'll be some of those. And let's take a look at our item parameters. These are our lambda values, and you can see these are all converged. So my trick worked. It all was in the right direction, right? And we have some that have very high values, 3.11. That's a very discriminating item. A little bit lower discriminating item. But this is less the point of this workshop is about describing what lambdas do. If we were in a traditional psychometrics workshop, we'd want to use these to our benefit. If you were curious about all the psychometric things with it, if you go to my class notes from last year, I'd take a Bayesian approach to test information functions and item characteristic curves and test characteristic curves as well, so you can see the variation in each of those based on your sample as well. I think that's a little fun, a little bit different. But we won't do that today. And finally, I'm going to create a model 3, and I won't run this, but I'll show this to you. I'm going to run the model where I estimate theta's variance. And then we'll have a break, and then we'll talk a little bit about model fit after break, okay? So I want to estimate theta's variance. So here, I put a parameter, theta SD. I said theta's variance, but I have to remember in STAN, the normal distribution's second argument is a standard deviation, not a variance. Yes?
Just a small one. When you're defining the identity matrix for the difficulty parameter, could you maybe test there for item dependencies?
You could, yeah. In the prior, no, but in the posterior, yes. So if you wanted to look at whether mu1 and mu2 were related.
Yeah, if you answered item I rightly, then maybe.
Correct. Yeah. I don't have that syntax here. I can over break. I can put it together and show a picture of it if you'd like. Like for some if you plot the posterior distribution of mu1 and posterior distribution of mu2, they'll see how interrelated the item parameters might be. But from a prior point of view, I don't know that we have a lot of thought of whether we should define a correlation or covariance between them.
That's true.
Yeah. So. Actually, every time I teach this, someone asks about that, and I'm always like, well, I've never been in the case where I could speculate. I don't have a belief on whether item 1 and item 2's intercepts should be related. I hope they wouldn't, but I don't know. So, okay, so theta standard deviation is the new parameter, but to do this, I need to turn off one of the loadings. So I take the very first item, and I remove it from the loop that I had for items before. And I just make my loop from the second item up to the 10th. So the very first item up here has the first item intercept, no loading, and theta. Okay? Then the only other difference is I have to do, because I have one fewer lambda, I have to take item minus 1. Because the vector itself starts at 1. So the first lambda actually refers to the second item. Right, so I have to make that the one catch. Theta's standard deviation, I'm giving a log normal prior to. Now, you talk about a big debate about, well, in my opinion, trivial things. Read about how to define priors on variances from about 10 years ago. It was like a 5-year battle between different groups of people who like Bayesian statistics. And it's all about what happens sort of in the limit. I'm going to just push that to the side. I use a log normal prior for 2 reasons. Number 1, this is a standard deviation, so it needs to be positive, and log normal is a positive number for a prior. Number 2, the log normal has 2 parameters, a mean and a standard deviation, which gives it a location and a scale, which means I have a little bit more ability to, if this were to have a problem being estimated, I could put more information on 1 or 2 of those values. Right? I can center the information at a spot on the standard, on the variance itself. Now I don't have that problem, and I try to use an uninformative prior here. Again, theta standard deviation, this is a real number, it's not a vector, but it has a lower bound of 0. If you do not put a lower bound of 0 in, Stan would be perfectly happy to estimate a negative variance and then break. It will actually give you a warning, and then stop. So you can't do that. Yeah, why did you let me? Anyway. Then I have to, because I defined a log normal prior, I have to submit in data its mean and its standard deviation. My data for this are right here. I actually use a standard, a mean of 0, standard deviation 1 for the log normal prior. It's relatively uninformative. And then, let's see. Thank you, GitHub Copilot. So let's run this. And let's take a look. Here, I also need to check for theta SD. Actually, theta, because I named my log normal prior theta SD, anything with theta in the term will be checked in my grep statement here. So let's see, convergence. 1.04. Ooh. Problem. Actually, that's not a problem. Anything usually less than 1.1 is acceptable. I like to see lower than that, but I have seen higher than that as well, too, in press. So 1.04, not as good of convergence as before, but I don't stress too much about that. I don't worry too much about that. Let's take a look at that trace of the item of the theta standard deviation. This might be the reason. This is less converged from before. That's starting to look suspicious. How many of you would say, I don't like that?
It's like a roller coaster.
This whole workshop is a roller coaster. Anyway, yeah, it's not ideal. It's not perfect, but at the same time, I think it's sufficient. We can also look at the value, and yet theta SD is where the 1.04 value happened to be. So that is the parameter that had a hard time converging itself. Alternative methods to try to get this to be a little bit better, although again 1.04 in review, like if a reviewer saw this, they would say, nope, this is not a problem. Yeah, it's not as nice as a 1.0, but it's still not better. And for whatever reason, 1.1 seems to be a standard, or 1.08 I've heard people say. So it's still within reasonable levels for what I've seen before. But a couple things to note here, because we've estimated theta's variance to be 1.58, you'll note the other lambdas. Now remember, this 1 actually represents item 2, right? But you see the scale themselves have changed, because the theta has changed. That means the lambdas have changed. And not only that, a little bit of the differences here in the mu's as well, too. That's why we see the changes as well. Questions on any of this? All right. Shall we stop here for break? Sorry, I overran break. All right. Let's take a break, and we'll come back. And I will stop recording.